Alright, welcome to another Draft Physics presentation. I guess this will be the first in probably a few videos regarding these mechanical universe videos. So, I've been through 25 of them and haven't found too much to disagree with. It's all been Newtonian and Galilean kind of stuff, and now it's moving into the Einstein bit. Just play this little bit. So anyway, yeah, that's how they start. And so right around here somewhere, 13, let me just say, is where it starts to get interesting, where they start bringing Einstein into the story. And this gets into the Eddington thing and what made Einstein famous, and it's a lot to disagree with in terms of what they're saying.
And if solved, the answer to perhaps some of the deepest mysteries in the cosmos. Like Newton before him, Einstein began with the law of falling bodies. Galileo didn't quite understand gravity. No one really would until Newton.
Well, let's be sure. Newton didn't understand it either, in the sense that he didn't tell you how it works. He just told you what it does and the laws that governed what it does. But again, there wasn't any understanding about what the force was. It was still just spooky action as far as Newton could tell. He knew there probably was a cause, but he didn't know what it was. So that's sort of to say Newton understood gravity is, reaching.
But he discovered the fact that all bodies fall with the same constant acceleration. Why should the
Okay, so, well, let me finish this question. Why should
the force of gravity lead to such a strange result?
Now, they say it's strange. Well, it's not really strange if, for example, you thought of it as being something that affects the matter in something, and it affects it equally. So the more atomically, the more atomic bits you have, the more the force is going to affect you, and therefore it will overcome the fact that there's more of you to move. So it would be directly inverse to your mass. The heavier you are, the harder you are to move, but the more force it's going to hit you because you have more mass to collect it. So if you understood mass as being a way of collecting force, that is, having more electrons and protons and neutrons, means that you have more things to be hit by the force, and therefore more force will hit you, and therefore because you're heavier, you're going to absorb more force. So it's not really unintuitive that everything would fall at the same rate, because everything's getting affected at rates proportional to how big they are. I mean, the truth sort of is that heavier things would fall faster if all they were heavier, and it wasn't the fact that they could collect more force.
When calculating the acceleration of a falling apple, the mass cancels out, leaving the same acceleration for any falling body. But why should that be?
Right, I don't know why they have the ME here and the RE, but whatever, it doesn't really matter. So again, he's asking the same question. Why should they? Well, because it's a nuclear force would be the first answer, the easiest answer. It's affecting the matter bits, and so the more matter bits you have, the more force that hits you. Therefore, the more it overcomes the fact that there's more of you to move.
Be the case?
It would be harder to push the heavy apple. If you had to push something, it's easy to push something light. It's hard to push something heavy. Well, obviously the force of gravity is doing that. It's hitting the thing that's heavy a lot more because it has more mass. So it's adding more force. So they sort of imply that the force is the same. Well, the force isn't the same. It's proportional to its mass.
In F equals ma, the mass determines how much force is needed to produce a given acceleration.
Exactly. So it's always a different force for everything. So the heavier it is, the more force I have to apply. There's a different force for every mass. And gravity's implying that there's the same force. Well, there's not the same force. It's a different force for every mass. And so he's going to say something now that just is wrong.
In other words, the mass determines how strongly a body resists changing its inertia.
So again, this changing inertia, it doesn't resist changing its inertia. So that's a way of saying something that's just the wrong way to say it. There's just more of it to move. Therefore, you need more force to move it.
This property of a body has nothing to do with gravity.
So again, nothing to do with gravity. It has everything to do with gravity, because that's exactly what gravity's doing. Heavier it is, the more force it applies, because there's more surface, so to speak. Mass is essentially a surface for it to hit. So it hits more surface, it applies more force, therefore it moves the heavier thing the same speed it moved the light thing, because it used a lot less force on the light thing, because there was less of it to hit. So again, they just, this whole resistance to thinking of gravity as an actual force instead of some imaginary thing. If they had to make it out of a real force, then they'd understand that the real force is going to affect, what's it affecting? It's affecting mass. And what is mass? Mass is electrons and protons.
It's called the inertial mass. On the other hand, in the law of gravity, the mass determines how strongly a body attracts every other body in the universe.
And again, it doesn't really attract. It just, again, the idea is the heavier you are, the more force you collect to be moved. And when you move towards something, you're blocking the force that would have moved it, and so it has no choice but to be pushed towards you because you've absorbed a force that would have hit it. So the simple argument is if one of these things moves towards the other, it's going to initiate, induct a process where they're going to keep feeding on the fact that they're absorbing forces that would have hit each other. So they're going to create a low pressure between them by absorbing force, that is moving, using the force to move. By using the force to move, the force didn't hit the other object, therefore the other object moves into the low pressure created.
This property has nothing to do with inertia.
So again, it has everything to do with inertia and has everything to do with its mass. That's why the mass makes something more gravitational. It's because more mass means it's absorbing more force. So.
It's called the gravitational mass. Isaac Newton understood that the law of falling bodies meant these two completely different masses had to be exactly the same for every body in the universe. But why?
So that sentence doesn't even make much sense to me. These two masses have to be exactly the same.
Why is gravitational mass always equal to inertial mass?
Because yes, it's the same thing, moving something. And moving something requires there to be some force, energy, to move it. Can't move for nothing, can't move by nothing. And the energy it takes is proportional to how much you have to move. It's not that complicated.
Could that be some cosmic coincidence? Scientists, as a rule...
Again, it's just ignoring the fact that it's a force. So if I push something, on a surface, I understand I'm applying a force. And they're just pretending that gravity's not doing the same thing. That there's not some real thing pushing. It's just a denial of the obvious fact. It's a push force. I mean, there's no attraction. There's just pushing. The universe is push, 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 push. There's no pulls anywhere. These people should have figured that out. Newton should have written somewhere, pull is garbage. There just ain't nothing. There's no such thing.
Don't place much stock in phenomena that can be explained by mere coincidence. Albert Einstein placed...
Obviously, there was no coincidence, because obviously it always requires force to move a mass, and it requires more force to move a bigger mass, and gravity applies more force to bigger masses.
None. He believed there must be some more profound law of nature that would make the law of falling bodies not a mystery, but instead something so simple it would be perfectly obvious.
Right, and there's nothing simple about anything Einstein suggested as a solution, so that's more nonsense. His answer doesn't simplify anything.
And the principle he chose became the basis for his general theory of relativity. It's called the principle of equivalence.
Right, and it's just like a wishful thinking sort of idea that, yes, of course, all accelerations require forces and they all require something to affect something, but the things that are affecting it are not all the same. So this is where you just have coincidental similarities, but they're not, there's no rule that they're all the same in any respect besides the fact that it takes more force to move heavier things.
Equivalence, that is, between constant gravity and constant acceleration. Imagine an experiment in which different objects with different masses all fall with exactly the same acceleration, called g. That might
Right, so they're all affected by more force. So the the anvil is blocking a lot more force to move down than the teapot or the apple. Therefore, anything here would feel less force. So as the anvil falls, it's absorbing energy that doesn't hit something down here, and something down here would feel more attraction or push from the environment towards it than the teapot or the apple. So the gravity is going to be proportional to the mass, and that's going to be a real effect. So there's a real consequence. This is absorbing more energy, this is absorbing less, and this is absorbing less, because of it's got less surfaces that are absorbing gravity.
might happen because
Less atomic surfaces, less electrons and protons.
the laboratory is on the surface of the Earth. But the same thing would also happen if the laboratory were far from Earth and everything else, say in intergalactic space. It would happen if the laboratory were accelerating upward with acceleration g.
Right, and it's just this is just a coincidental, looks the same, but obviously isn't the same. So we have no gravitational force. All we're doing is applying a force to this shell of the spaceship and moving the shell of the spaceship into the objects. So, there's no surprise that the shell of the spaceship, the floor, applies the same force to everything because obviously it's the same material. And so yes, the floor arrives at the same time to all these objects. It's just not even, it's so trivial a similarity that it's not worth saying that this has anything to do with the same science.
All the objects inside, obeying the law of inertia, would not accelerate. But they would all seem to fall with the same constant acceleration.
Right, so looks alike but ain't alike. That's simple.
Albert Einstein understood that the law of falling bodies and the mysterious equality of gravitational mass and inertial mass would be perfectly explained if the following fundamental principle were true. No experiment of any kind.
And so this proclamation just means nothing. It adds nothing to science to proclaim something that has no significance. And it has no significance, this proclamation, this prediction, whatever you want to call it. It just doesn't mean anything, and yet it's such a bold claim in the sense that you're presuming to know what all the possible experiments could be and how they could detect something. It's just, to me, this is a demonstration of not only useless physics, but just let's make up physics for circumstances that can't be proven. So it's almost like a religion.
Done entirely inside that laboratory, could determine whether the objects fall because of the pull of gravity or because the laboratory is accelerating upwards in outer space.
So this gives me some insight. I've been asking the question, why did Einstein bother doing this make the speed of light twice as affected by gravity? Why did he make photons twice as affected by gravity? And the answer is ironic. It's because of this stupid proclamation he made. To make his thought experiments fit his stupid proclamation that he should never have made, that is, his prediction that no experiment could detect whether you're in a moving spaceship or whether you're in a gravitational field. Yeah, experiments can detect it, and so to make it so it's true, even in spite of those facts, he had to make photons gravitationally affected, because that's the only way for him to create a consistency. And that's what you'll see here.
The idea seems almost too simple to be true, but Albert Einstein didn't take it lightly. Instead, he asked how the experiment would come out if it were performed with a beam of light.
So this is the part that's, this just points out this is exactly, it's this stupid notions that created this fake understanding. But let's go to it.
Laboratory out in space. The answer was easy to see. If the rocket accelerates upward while the beam goes straight across, it must seem to...
Okay, seem to bend. So there's another tricky part to this thing. Like, obviously the light doesn't bend at all. It goes dead straight. So this really should be drawn as a series of straight lines. Okay, staircase. The light goes straight. It doesn't curve. There's no curve to the path of the light. The light went dead straight and the ship moved away from it. So they should draw this as the ship moving and the light going straight. They shouldn't draw it as a curved line because it doesn't really curve. The ship moves away from where the light was, so they should just move to show whether the emitter goes down and the target goes down. There's no curve in the light. The light does not bend.
To bend downwards, just a tiny bit. But then what would happen on Earth? The answer comes from the principle itself.
So this is again on the rocket ship. It's not Earth. And again, the way they drew this, they should have the ship, they show the movement by the flames coming out, but the ship doesn't actually move relative to this line. So they made the line bend instead of the ship move away from the line. The ship just moves away from the line. That's all that happens. Just like the teapot didn't bend, nothing else bent before, so they just drew it wrong.
Since no experiment, not even this one, can tell whether the laboratory is on Earth or in space, the result must be exactly the same.
Right. So, because he knew light was going to hit below, so in spite of what people say about relativity and light jumping forward, clearly Einstein thought it would end up below. And so now he had to make it match on Earth. So he had to make gravity move the photon down so the two would match. So this is like the opposite of what they claim Einstein said, in the sense that clearly Einstein didn't believe that the beam goes forward. He's clearly arguing that the beam falls, and because the beam falls when the rocket moves, the beam must fall when it's in gravity, or the two things won't match. So I'm just pointing out to these people who keep talking about how Einstein's theory says the light booms forward. Well, not by this description of what Einstein was saying.
In other words, Einstein concluded that light doesn't travel in straight lines. Instead, it bends ever so slightly because of the gravitational force of the Earth.
Right, and he did that to make it fit his thought experiment about what would happen if the ship is moving when a light beam goes across. So you shoot a light beam, the ship is moving, and he knew, like say if he had a hole in the ship, and so it's an external beam of light and it goes through the hole. He knew that the ship is going to move and the light beam is going to keep going straight. So he knew it's going to hit lower on the ship's surface. So now he had to make that lower on the ship's surface thing match what would happen on Earth. So he had to make photons moved by gravity.
Einstein predicted
For a principle, to validate a principle, he should have never boldly gone he should never have jumped so far ahead of what he had any evidence to prove that all acceleration is the same, because it's not. I mean, not that the acceleration isn't the same, that you can't do an experiment to prove what's accelerating when you can do such an experiment. And the light is a perfect experiment for it, because it will show you, if you're on the ship, that you're moving, because the light will essentially be a speedometer. The faster you go, the more the light will end up hitting lower than your target.
Light would likewise bend as it passed the sun. And when he said so in this letter to George Ellery Hale, it looked extremely good on paper.
Right, but the problem was it's not enough of a bend to fit what happened on the spaceship. So that he was stuck and he had to double this number. So instead of the arc, the amount of arc being 0.784, he had to boost it to 1.24. He had to double it, or whatever the doubling is of an arc second.
But not quite good enough for astronomers to risk their precious telescopes, much less their precious eyesight, looking directly at the sun.
Right, but now we have the technology to go into space. And in space, there's complete black around the sun. There's no effects of the atmosphere screwing up your observation. So you can look right at the edge of the sun, without looking at the sun, just looking at the black space. And somehow they haven't been able to do that experiment. With all that technology that flying around up there, not one of those satellites has been able to demonstrate our sun lensing.
And so, George Ellery Hale, Einstein's correspondent, and himself one of the great astronomers of the early 20th century, made a gentle suggestion. Why not observe the sun during an eclipse?
So in other stories, they say Eddington thought of that, so they don't get that history right.
And in 1919, that's precisely what Sir Arthur Eddington and his party of solar explorers went out and did. The triumphant success of that expedition.
All right, the triumphant success of that expedition, right? When the guy wrote in his own journal, I wouldn't stake my life on these results. He pointed out how the weather conditions were horrible. His images were 1/10 the quality he was hoping they would be. So where he thought he was going to get a nice photograph of 10,000 stars, he got 1,000. I mean, it was 10% of the quality he was hoping for. And, all this glorified talk about how brilliant the experiment is. Now lots of other stuff has come out about how some of the slides didn't match, so they threw those out. This is just bullshit history.
Was the first great proof of relativity.
So again, it doesn't prove relativity, doesn't prove any of this stuff. All it would demonstrate was that, photons are affected by gravity. That hardly proves that you can't do any experiment to detect how fast you're going. And it certainly, now you're stuck with two new problems. Why do photons affected twice as much by gravity? So Einstein's new number that just is pulled out of the, I just need to do it because nobody can do the experiment unless I cheat, essentially. For what reason? There's no logic to it. Photons aren't charged. Photons aren't in any way mass. Doesn't seem to be something they do. So why do we assume they're going to be affected by gravity at twice the rate of any other material body when they seem the least affected?
Turned the quiet, shy Albert Einstein into an instant, world-famous folk hero.
Right, so this is some sort of about mythology and popular memes, and it has nothing to do with the real hard legitimacy of the science.
Everyone knew about him, even though few could understand relativity. And no one really knows why the world took Einstein to its heart. Probably, exhausted by World War I, people needed a hero.
Right, so science allowed pop culture to decide what was good science. That's what happened. I mean, the scientists should have been serious enough to say, we're not going to let pop culture just define our science. And instead they did. They just said, oh, this is really cool. You get popular, you get Nobel Prizes, it's all fun, fun, fun. So yeah, let's let pop culture decide what is good science and what's crap science.
His discovery was benign, and Albert Einstein...
Yeah, his discovery was irrelevant to almost any part of physics you could imagine, but it does create, in some respects, I mean, it's an effect that doesn't affect anything, in a real world. Saying photons are bent by gravity doesn't mean too much in most of physics. It's not going to change anything. But it's still a statement, and it's a statement you should have a burden of proof. And the proof is garbage. The proof stinks.
Einstein looked like everyone's favorite uncle. He also became the symbol for all scientists, and it didn't make any difference that few could understand Einstein's great work. The principle...
So they keep saying it's a great work, and they keep supporting it, and keep talking about how it's a little bit too incomprehensible. And again, where does it all come from? Where did all the complex field equations come from? Well, he was given the challenge by Eddington to create some theory that explained Mercury's precession. So he reversed engineered a formula that ends up with the result. And the formula is so complicated that nobody knows what's making it happen. It's all lost in the gibberish.
Of equivalence raises an interesting question. If light travels curved paths, what is a straight line? Einstein...
Well, obviously the curves would only be incidental to the gravity, so they're bent. They're not curved. They're deflections. They're not curves. The light doesn't keep curving somewhere. It's changed in direction and then it goes straight again. So it's not even you don't break straight lines by conceding to moments where things curve. I mean, a straightaway on the racetrack is still a straightaway. It's not an...
Einstein said that it makes no sense to talk of straight lines. Space itself is curved. Not only space, but space-time.
Yeah, well, that's just nonsense. It's not curved unless there's matter to curve it, so that's wrong. And there's lots of empty space with no curves in it. So, no substantial curve.
That means that space and time change as they move through gravitational fields.
So again, the bold leap that somehow we're going to connect time to the rubbish of gravity, and this whatever notion of gravity, that it's just about curved lines and we don't need to have a force that actually makes the object move. So everywhere else in the universe we know there has to be a force. We can't use a curved line to get the shuttle off the ground. We have to apply a force. So it's just there's no continuity in this explanation at all. And then connecting it to time is just, again, the simple explanation for the effect on what we call time is to point out that time is completely clock dependent. So if the mechanism of the clock is altered, if I put a pendulum clock underwater, let's say, I don't know, we could argue that it's not going to swing as fast. Lots of things can change. The physical environment can change how well a certain kind of clock performs. And that's all we're really saying then, is that, okay, you can break some clocks mechanically by giving them velocity. That velocity affects certain physical functions within atoms. And that's all you're talking about. You're just talking about the fact that a few incidental things change. Time itself isn't changed. How you age, how your biology is affected is going to be completely different than how the atomic cells are, atoms are affected. So there's no continuity in this. There's no reason to expect that because a GPS atomic clock is affected by velocity, that a human being would be affected exactly the same way, and that you'd age slower, or that any of that crap would happen. There's absolutely no evidence that would be the effect.
Fields. But how does that relate to Newtonian physics? In his laws of motion, Newton said a body moving in a straight line will keep moving in that straight line until it's acted upon by an outside.
Right, and the outside forces are all over the place because there's gravitational bodies everywhere, and so to some extent Alpha Centauri is affecting me. Yeah, the effect is tiny, but it's there, it's real, it's once in a while, a photon heading for Alpha Centauri is blocked by me. It doesn't go there. And so there's less force, and Alpha Centauri moves a tiny bit towards me, and then when it does that, it absorbed a force. Now I don't get hit by that photon that would have gotten to me, because Alpha Centauri absorbed it to move. And yeah, so there is a relationship, but it's very thin, weak.
Force. If there are no straight lines, what is the meaning of the law of inertia?
So again, they're all straight lines. And on the real scale of the universe, where billions of things are happening in every second that we experience. Every second we experience, there's trillions of things happening, events. And they're all happening in actual straight lines. And all of that stuff looks like a curve to us because we're way behind. We're not really seeing the staircase that's really being traveled. So we don't see what it actually did. We just see the end result, which is here, and we draw a curve.
On a flat map or chart, the shortest path between 2 points is the familiar straight line that joins them, but not on the surface of a globe. Here, the shortest path between 2 points is not a straight line, but is a great circle.
It's a great circle. It just doesn't make any sense. Obviously, if you have to go around the object, then it's going to be a longer line too.
To generalize, the shortest path between any 2 points on any surface is called a geodesic.
Yes, and it's no such thing in space. There's no geodesic obliging something to travel a crooked line. Photons going from one place in the universe to another place in the universe travel a straight line.
Einstein said that starlight may not really be bent by the gravitational force.
All right, starlight may not really be bent by the gravitational force. Why would he say that when he's saying exactly the opposite? But let's go a little longer.
From the sun. Instead, it can be said to travel inertially along the shortest path between any 2 points in the local curved space-time.
Right, so the same difference. Just saying, oh yeah, it travels a straight line, except there's a gravity in the way that causes it to bend. So again, it's a straight line if there's no object in the way. But again, there's just no evidence of this bend. None. No real hard evidence that this ever takes place, that photons ever do this.
That makes it seem to bend to any observer. And for the same reason, the Earth's orbit doesn't have to be, as Newton said, a compromise between inertia, which makes the Earth want to fly off in a straight line, and the sun's gravity, which keeps the Earth circling the sun. Just like...
Well, that's all it actually is, though. You can't deny that that's the truth of it. There's a force, and they just keep pretending. They won't use the word force. They won't understand there's a force. Something's pushing. There's no other way to explain it. And pushing perfectly explains it. A particle gravity perfectly duplicates the circumstance. It provides the necessary variable amount of force will be applied based on your mass. So if you just create something that absorbs force based on its mass, this is the result you get. Now, we can make cheap mechanical models where it's just observed on its surface and its surface isn't related to its mass, but the same effect will be realized, and it's a real thing. Mach gravity works, and yet they don't even suggest the possibility that it's a push force, even though Mach gravity works.
The light, the Earth can be said to move inertially, without any forces, along a geodesic and the local space-time created by the sun.
Right, so this geodesic doesn't mean anything, right? Because we presume the line to be bent by a artificial circumstance of mass existing. It just doesn't say anything. It's not an explanation of how it happens or why the atoms are affected. Why do the atoms move? No explanation, because they can see geodesic lines. I mean, what's the explanation? There's got to be a physics to this physics. There's nothing physical in this explanation. It's just so empty. It's just spooky action, spooky geodesic.
Sun's presence. In other words, curved space-time, or even just curved space, can create the appearance of a force even if there is none.
Yeah, right. It's just a drawing that shows you what the inverse square law does. The fact that the force is proportional to the distance in a specific way. I guess I better get that. Alright, should be back and such.
Imagine two beings starting out on a journey, obeying the law of inertia, on what they think are two straight lines. But since they're on the surface of a sphere, they're really great circles.
Right, this is just saying, so, and pretend you have two lines that start off straight, and you have a gravitational body here. Yes, they're going to both bend towards the gravitational body. I mean, wow. I mean, the gravity will push evenly and cause them to curve. Again, it's not an explanation of how it happens at all. It doesn't give us anything more. It's just it's a way of rendering the inverse square law in geometry. And that's all it is. It's just a render of the inverse square law.
After a while, they start getting closer together, as if drawn by some mysterious force. They might even call that force gravity. Einstein.
Yeah, yes, by a mysterious force. Mysterious, they're all mysterious in the sense we can't see them. Again, you don't see a lot of the forces, right? I mean, the force when the space shuttle takes off, or rocket. Big giant flame going out one end, you don't see the force that goes in the other end. You don't see the equal but opposite reaction in the sense you don't see any force, but clearly there is one.
Did exactly the opposite. He eliminated the force of gravity.
Exactly, yes. A complete disaster.
Can be replaced by the curvature of space-time.
And again, just to keep saying the curvature of space-time, there's no curvature of space-time as a thing. There's just dimples in space created by this geometry. But it's just, again, in 3 dimensions, you can't even draw it as curves. Because it doesn't curve in 3 dimensions. The force doesn't.
But Einstein now had created a mammoth dilemma. How does mass cause space-time to curve? He spent the most...
Yes, right, exactly. How does mass, by itself, without a force, spookily action things?
Difficult 7 years of his life, from 1909 to 1916, working on the riddle. And when he finished, he had produced nothing less than a new theory of the cosmos.
Again, it's not a new theory. It's still the inverse square law. It's still spherical objects. It's still the same rules. It's, you know, just amazing hyperbole here.
It was a theory that was not designed to extend or expand Isaac Newton's mechanical universe.
And it didn't.
Instead, it was designed to replace it completely.
And of course it didn't.
But how could that be possible? Could it?
Yes, that's right. You can't undo it. The inverse square law. All you can do is draw it a different way. That's it. It's just about drawing a force a different way. And it's not even drawing it a different way. Like I said, in 3 dimensions, if they draw the force, the thing causing the effect, as just straight lines coming into the center of the gravity, you get a curve, a proportional curve. You get the same exact curve if you use straight line forces coming from the outside. Photons.
might be that Newton's theory was wrong after all. Does the moon not fall 1/20th of an inch every second? Do planets not still sweep out equal areas in equal times?
The point is to have a reason why. What makes the atoms of the moon move? You have to explain why the atoms themselves move. Why the little bits inside say, I'm going to go that way, or I'm going to go this way. If they're going to do that, if they're going to change their path, the change has to be created by something. Newton's laws still apply. If the electron's going this way, and all of a sudden it's going this way, you have to apply a force. You have to explain why it changed its direction. And this relativity crap doesn't do that.
And when a spacecraft leaves the Earth, who's driving?
That's a good question. I think Isaac Newton's doing most of the driving right now.
Of course, Newton's laws work just as well as they always have.
Right, so Einstein didn't undo them, didn't create a new physics.
In most places and most times, Newton's universe and Einstein's universe are so nearly identical that only the most precise instruments of science stretch to the limits of their abilities.
Right, stretch to the limits of their abilities, which is an important thing to remember here, okay, is that you're stretching credulity in a sense, the credibility of your experiment by stretching, by making the thing do what it's not its optimum range, making it work at a temperature higher than it usually works at. Yeah, you're stressing it. And then you take the evidence under stress and say that's good enough. That's, we have enough evidence. And way short of enough evidence to make all these presumptive statements, these statements of conclusion based on weak evidence.
Can detect the tiny differences. But there are times and places in the universe where conditions are so extreme that only Einstein's theory can explain them.
Right, and this is just more crap. Because they're going to start talking about black holes. And, we have no experimental evidence. We don't have anything to put on the table in terms of, well, here's data that we collected. There's no data. So this is just all some sort of made-up crap.
For example, when a very large star, much larger than the sun, exhausts its nuclear fuel, it starts to collapse under its own gravity.
So this is their own declaration of why something supernovas. They have very little evidence to base any of that on. It exhausts its fuel and somehow collapses under its own gravity. Well, how exactly does it do that? I mean, why? Why does that? How does that happen exactly?
Mass is blasted away in a violent explosion, but with no force strong enough to oppose the collapse. The inward fall of the rest continues until gravity becomes so intense that space-time itself...
So somehow there's an opposite reaction is what they're kind of saying. Because the stuff blew out, something blew in. No, that's not how explosions work. The stuff going the opposite way. Like when something explodes, the stuff goes forward and stuff goes backwards. So you already had your opposite reaction. You can't claim another opposite reaction where they pushed in against each other. So they've perverted the equal and opposite reaction by separating the two events, by saying the event shooting this way and the events shooting that way are not the same event. So they've taken one event and separated it to create some notion that this still needs an opposite reaction, so it has to go in. And this one needs an opposite reaction, so it needs to go in. So these two things are going in. See, and it's just a way of perverting it. If they put the two action and reaction together from the center of the gravity's perspective, there's no need for this black hole to be created.
Itself is stretched and warped into a point of infinite curvature.
Which means nothing. Infinite curvature. What baby talk? Infinite anything is baby talk.
Called a black hole. like an ordinary projectile falling back to Earth. Light itself and absolutely anything else is drawn back by that awesome concentration.
Right. Physicists don't even believe that crap anymore. So, that light can actually be bent by the gravitational force of a black hole, because they still have to deal with this fact that there is no evidence that you can slow light down use gravity to slow it down or gravity to speed it up when it's moving in the direction of the gravity. It's only a tangential effect. So gravity affects photons in another unique way, where if it was an electron, the electron will gain velocity as it moves into gravity. Photons can't do that. And an electron leaving, will lose velocity as the gravitational force affects it. They can't do that with photons. So, all these inconsistent laws, is just evidence of, Houston, we have a problem. And they have a problem for 100 years and they don't fix it.
Of mass. It takes an immense amount of mass crowded into a tiny space to create a black hole. If black holes exist...
Or you could take a lot of mass and put it in kind of just an average amount of space, and we wouldn't be able to tell a difference from a distance. From a distance, we couldn't tell whether it's a black hole or just a heavy thing. No way for us to tell.
Exist. They are either remnants of collapsed giant stars, or they may be primeval.
Right, so now, just a minute ago he says black holes were created by supernovas, and now he's changing the story. So let's go back to this.
And absolutely anything else is drawn back by that awesome concentration of mass. It takes an immense amount of mass crowded into a tiny space to create a black hole. If black holes exist.
So he says, if black holes exist, he just told us they exist, the supernovas create them.
They are either remnants of collapsed giant stars, or they may be primeval, left over from the Big Bang. The instant.
So more we just make that up too. Created how? Through what process?
Instant when the universe began.
Alright, so that's the story. I don't know, maybe I didn't pay attention. They end all the videos with us going back to the lecturer, so I don't know. I haven't seen this part, so I might as well play it.
Of course, it's tantalizing to try to imagine what it would be like to be inside of a black hole. But we'll never know. That is the ultimate impossibility. Oh, you might arrange to fall into one if you really tried. But then, even if you survived, there'd be no way for you to let us know what you found once you got inside.
Well, unless you figure out a way to get out again.
But here's something to think about. When the universe was created in the Big Bang, it started to expand rapidly. Clumps of matter condensed into galaxies, but those galaxies are flying away from each other at great speed, even today. But that expansion does slow down with time. After all, the galaxies do attract each other by means of gravity.
Yeah, well, whatever. You just said they're moving away very fast, so the amount of gravity is getting weaker as they move further and further away from each other, and the amount of time it would take for their gravitational pull to undo their momentum seems preposterously long.
In fact, if the density of matter in the universe is high enough, that expansion will not continue forever. Someday, the universe will start contracting again. It will become smaller and smaller.
Right, so there's no point in playing this. So this was made back in the 70s, I think. So obviously they've changed their theory since then. And I think the popular notion is that it's going to die a heat death. Everything's going to just expand out of reach. So anyway, until the next time and such. So anyway, yeah, I got through 25 videos without finding much to complain about, but this one is, like I said, this is where it starts to get into the wacky Einstein error physics, and everything turns to crap. So I'll probably be doing a few of these, but we'll see. It looks like the next one gets back to spheres and more mechanical stuff. well, beyond the mechanical universe, beyond the mechanical universe. Even though the series is titled The Mechanical Universe, it's kind of funny. So anyway, we'll see how it goes. Let's see when I'm next triggered to say, no, people shouldn't believe this crap. Not the right answer. It's not the right answer.